What I'd like to do today is talk about generating gridded and contoured maps in GeoGraphix with IsoMap and GeoAtlas. I'd like to show you some tips and tricks, including hand editing contour maps and contour to grid operations. Okay, so let me kill PowerPoint and let's get going. The example I'd like to show you today derives from an area in southeastern Kansas. It's actually some geology that I did with the Kansas Geological Survey back in the late 80s and early 90s when I was looking at the Pennsylvanian section in that part of the state, southeastern part of the state. And I just wanted to show you a quick screenshot put together in our geomodeling cross-section package of the geologic section I want to talk about. This is a portion of the Missourian section within that part of the state, and the unit I want to map in particular is this carbonate here, outlined in blue. It's called the Snyabar limestone. This is the top here, and the base here, the two blue picks. And you can see that below that the correlations on through-going black shale markers are pretty layer cake. However, in a lot of these cases, in these cyclic successions, you do get a fair amount of stratigraphic variability, particularly within some of these upper carbonate members. So I wanted to go ahead and in my working area show you how I would map this Snyabar limestone, and then I want to tweak the map, tweak the contours, hand edit the contours, show you some tricks there, and then talk about contour to grid operations. And then after that, I have another example from a different part of the world that I actually ran into at a client site that I'd like to share with you because I think it shows you some interesting tricks as well. Okay, let me minimize this. So I showed you the stratigraphy. This is the area. These are townships, so you get an idea of the scale that we're working. And I'm just going to go through the creation of a gridded and contoured thickness map of that Snyabar limestone. So I'm going to start by going Layers, up here in GeoAtlas, Layers, Create Layer, IsoMap. And my options are build surface, grid operations, contour to grid. Well, we're building a surface from XYZ data. And the first thing I'm going to do here is I'm going to name the layer, of course using my initials, best practices, right? There we go. Snyabar isocore, and I'm going to go ahead and add a data source, in this case from wellbased, but I just wanted to hit this drop down and show you all the other options that you have. Some of these are actually pretty intriguing. For example, using an existing layer as an additional data source can come in very handy, particularly in situations where you may not have a lot of control, let's say on a zero contour. And what some folks will do is they will actually create a blank IsoMap layer, lay it on top of their geology, and then draw a zero contour line on that blank IsoMap layer and use it as a second data source in addition to their, let's say, well-based data sources. So in that way they can more closely control their zero contour. So that's just one example of the use of additional data sources here. In any event, we're going to do a relatively simple map in this case. We're just going to use a well-based data source, and I'll go ahead and say OK. We're going to go ahead and go to the formations table, and we're going to choose isocore top to top. Notice there's an isocore top to base, which when I'm working with new users they always go for. Well, it turns out that the base of a particular formation in wellbase is usually not defined because there's no way to pick bases in any of the cross-section tools that we have. So typically what you'll want to do if you want to do a thickness map of a unit, or perhaps use petrophysics or zone manager to examine a particular stratigraphic interval, is you need to pick the top and the base of that unit as tops. Okay, if you need to get bases in there, you'll have to either hand enter them or probably bring them in via a spreadsheet import. But again, IsoCore top to top is the way to go. And I'm going to choose my top SNIA bar and my base SNIA bar, and I'm going to throw my three sources here that I've got in my private strat column over into the selected sources. One of the nice things about this dialog in terms of creating gridded and contoured maps is that you can select the sources specifically that you want and put them in the correct hierarchy. You don't have to necessarily abide by the hierarchy that you've set up in Source Manager. So in that regard, it gives you a lot of flexibility. Okay, so I'm going to go ahead and say OK, and it's going to read the data in my project or active AOI, and you notice I've got 604 data points with an average Z value of about 45.5 feet with a range of 2 to 80, so we have a pretty good thickness variation, so we should get an interesting IsoCore map here. By the way, if you happen to see any outliers, there's a couple things you can do. So for example, if I had a messed up correlation 400 feet and I knew that was wrong, I could either use a z-value filter and say I don't want to map anything greater than 100 feet, let's say, because I think that's bogus. Or alternatively, you can select the data source up here in the grid and go edit data. Here's all your XYZ data, and you can sort by clicking the Z column, sort on the Z's, and you could actually scroll down and nail that 400 or whatever right here and be in the bottom row, and you can delete that. It doesn't affect the database, but for a if the boss is breathing down your neck, you need to get this map out in the next 10 minutes, you can quickly get rid of that data point and then come back later when you have more time and figure out exactly what the problem is. So that's another little trick you could use. Okay, so I'm going to go next, and we're going to look at some more of the options that you have with regard to creating these maps within GeoGraphix and IsoMap. Okay, now the gridding algorithm is set by default to minimum curvature, which in my experience and the experience of a lot of our users works pretty well. But we do have a lot of other options, as you're probably aware. For example, you can make trend surface maps, first to sixth order trends. So if you have the mind to make a residual map, you could use trend surface mapping, make a first order trend, and then subtract a structure map, for example, or an IsoCore from that to look at local variations on the regional trend. We have adaptive fitting and other algorithms. I'll hit the other, and you'll notice we've got quite a few: triangulation, weighted slope, weighted least squares, etc. Now, what I generally tell people with regard to diving into these different algorithms and understanding them is that our help files, which are generally, in my view, quite good, provide a pretty good summary and some detail on these different algorithms. So when I click on help in that particular dialog, in the tab pages section here, I've got a gridding algorithm hot link that I can go to, and as you can see here, it actually discusses each of these algorithms, including our default, let's say, minimum curvature. Let me pop that guy up. So it goes through and gives you a little bit of technical detail on how that particular algorithm works, and maybe just as importantly, it talks about some of the parameters you can use. For example, radius of influence, right? What does that do? How is it defined? How is the default radius of influence decided on by the software? It tells you exactly how that works, and it also gives you a little bit of a discussion of why radius of influence can be important. So for example, if you're mapping an area where you have maybe discrete thickenings, carbonate buildups like Silurian reefs in the Michigan Basin, where you have, I don't know the scale on those things, maybe a quarter mile across. You don't want them to be influenced. You don't want that mapping of those pinnacles, let's say, to be influenced by the thinner areas. You can just decrease your radius of influence, which will effectively more and more isolate small groups or clusters of data points. In fact, if you want to get silly, you can drop your radius of influence to a very low value and you'll end up with little closures practically around every data point. So you can be a bit iterative about that. You can play with something like the radius of influence to see how it affects your map until you get the result that you're kind of expecting geologically. Okay, so again, the help files on the gridding algorithm can be very, very useful. I think there's another one I wanted to look at, for example, weighted least squares, and it will actually give you some tips on maybe when you want to use weighted least squares, when you want to get rid of maybe unwanted noise in your data. So again, you can go through the help files to learn a little bit more about these different algorithms, because we do get a fair number of questions on which algorithms to use. Okay, so I'm going to go ahead and stick with minimum curvature and the other defaults and move on to the grid spacing tab, which is a biggie. Okay, now in terms of grid spacing and smallest feature radius, the smallest feature radius is tied into sorry about the noise here. Smallest feature radius is tied into the columns and rows. So essentially, when you change smallest feature radius, you will essentially change columns and rows. In general, the default value for smallest feature radius is too large. It defaults to 400 or 500 grid nodes, as you can see, and unless your data are really widely spaced, that's probably not enough detail in general. So what I like to do is have an idea of how closely spaced my data points are in areas where I'd like to see some detail, and then go ahead and adjust the smallest feature radius. So for example, I've got some clusters of data. I'm drawing a little circle or down here below the dialog, if you can see it, where these red wells, these are all the wells that have Sniobar top and base, where these red wells are clustered pretty closely together, and maybe I want to get a lot of detail in there. I can go ahead and set my smallest feature radius to something like 500 feet, and then I can click in the column, one of the columns and rows boxes, and it will update, and then I can do a quick multiplication to figure out how many nodes I have. And the reason I want to do that is because in general, in the current iteration of IsoMap, you probably get away with between 15 and 20 million nodes. Okay, excuse me, that's been my experience. Implications there are if you're mapping a very large area, because IsoMap will grid within the entire active project or AOI. So if you're mapping a relatively large area and you want to do it in great detail, you may find out that you've created way too many grid nodes and you'll get a memory error. Okay, so the answer there typically is to create an area of interest that encompasses just the part of the region that you really care about, so you can actually crank down really the smallest feature radius and get a more detailed grid. Alternatively, if you have to map the whole area, you're going to have to change the smallest feature radius and make it larger, so you don't get more than about 15-18 million grid nodes. Got a bit of good news on the horizon though, and I've actually been testing this on my test machine. Our 2019.3 release, which is due out before too long, no promises here, actually contains a 64-bit version of IsoMap. And of course, 64-bit processes can access more RAM than you can put on your machine physically in general, terabytes or something to that effect. And my record so far, and I haven't really pushed it too hard, is a map containing 57 million grid nodes. So the implication of the next release with regard to IsoMap is huge in terms of being able to do very detailed mapping of much larger areas. So that's something to keep in mind. Okay, so again, when you're mapping and you want some detail, pay attention to the smallest feature radius, because the default is too small. Okay, and once you set that, if you don't want these parameters, this particular set of parameters to change, you can always lock your grid parameters right here with this little checkbox. The third tab is the geologic tab, and that includes an area where you can do surface substitution, The default is to simply, and this is in areas away from data, right? You don't want crazy edge effects on your contours, so the default is the average value roughly of your data. So it's going to use an average value of 45 feet in this case, which is about midway between the 0 and the 80 something. Alternatively, if you have a shallower surface that's more or less concordant with the surface you're mapping, you can designate that surface as your substitution surface, and the shapes of the contours, in this case the Snaiabar isochord contours, will more or less conform to that surface. Okay, you have that option. Bias trend, so for example, if you're mapping tidal ridges, oolite buildups, reefs, whatever, and you have you're interpreting a particular orientation, but you don't have maybe enough hard data to force that orientation, if you will, you can use a bias trend, direction and magnitude, to more or less have IsoMap inject your geologic bias in terms of the trends of the say sand bodies that you're mapping. And then z-value projection allows you to pull or push your, let's say, 0 contour closer or farther away from the actual 0 values. Okay, so that's what those guys are all about. Okay, let's go next. Now we have the 3 of 3 dialog, last dialog before we finish our map. The defaults here are to show the data points. Okay, and you can click on options, you can change what the data point looks like, etc. You can always do that later using layer display attributes. The grid is not going to be displayed, but again, you can display it later on if you want. Contours, of course, are going to be displayed, and you have options here. But again, you can take a look at your map once it's created and say, I don't like the way it looks. You can go back into layer display attributes and monkey around in there. And then there's the color fill options, and I'm going to go ahead and check color fill on. And at this point, I'm going to leave it as color density, which is the default, which fills the grid. Again, you can choose different spectra, you can edit or create new spectra, you can override the defaults and change the colors. So for example, if you don't want any colors, maybe you want it all to be all white where it's thinner than 5 feet, you could override the defaults and set these guys to white, etc. A lot of functionality there. Later on we'll do color fill contours, we'll talk a little bit about that. Okay, again, color density fills the grid. The colors are a little more smeared out, as you'll see here shortly. Boundary polygon, I'm going to create a new boundary polygon. Essentially what that does is it draws a polygon around the data and does not contour outside the data. Okay, so you don't have to even worry about edge effects if you use a boundary polygon. Those boundary polygons are editable, so you're not locked into the one that it creates. You can go back, edit it, and regrid, and then you'll get the contours filling up your new boundary polygon. A common misconception among our users is that the boundary polygon controls the area that's actually gridded, and that's not true. The entire active project or AOI is in fact gridded, but all the grid nodes outside the boundary polygon are set to null, so that's the way the software handles that particular issue. In addition, and you can only have one boundary polygon per map, per layer rather. In addition, clipping polygons an option. You can have more than one clipping polygon, and you can actually map either inside or outside clipping polygons. So for example, if you've got a little area where you've got 3D seismic, you could take that grid, contour that seismic, grid and contour that seismic in our seismic package, and then draw a clipping polygon around it, so that, and then say map outside, so that your well-based data are used to map outside the clipping polygons. You've got a very detailed seismically generated gridded contoured map inside your area of your 3D survey, and outside you're using well-based data. So clipping polygons can be very, very useful in that regard. Okay, now I'll go ahead and hit finish and let it do its thing. Just enough time hopefully to grab a swig of coffee here. Again, taking a little longer than if I'd left the defaults, but it's still not bad at all. It's going to contour pretty quickly. Now you'll notice that that map that's generated looks a little bit hideous, so clearly my contour interval is probably too tight. I'm going to right click and update the active layer. Could also have done it up here in the layer selection dialog. I'm going to override my defaults here, and sure enough, a half a foot, I don't I don't like that contour interval, I'll just override it to 5 feet and I'll recontour right here in my rebuild option. Finish. We'll see what we get now. Okay, much better. There's my Sniobar isochore in the area in southeastern Kansas where I have data. Notice the boundary polygon being drawn around there, and you can see that with the hot colors being thicks and the darker shades of blue being thins, you can see that in general we're thinning to the east-southeast down toward the basin in Oklahoma, or down toward the southern border of Kansas here. One comment I want to make, I keep using the term isochore, and I actually learned the difference between IsoPack and isochore because our option is defaults to isochore. That's a true vertical thickness map, right? An IsoPack is a true stratigraphic thickness map. If you want to make a true IsoPack, you can do it. I'm going to pop Zone Manager up here and show you that trick here real quick. So there's Zone Manager. What I've done here is created the Sniobar zone in Zone Manager based on the top and base of Sniobar. Edit zones. There's my Sniobar zone. You can see if I say edit, you can see how it's defined there. Okay, so and then I went ahead and calculated all the XYZs, etc. Then I went to a tool called Compute TVT TST Data, and I said, all right, I want to do a true stratigraphic thickness map. And to do that, you need dips, right? So what you do is you reference an IsoMap layer, and the software Zone Manager will calculate the dips at each well location and give you a true stratigraphic thickness. Now, in this case, and of course that's very significant where you have 10, 15 degree, 20 degree dips. When you have very low dips like you have here in southeastern Kansas, it's not so critical, so your isochore approaches an isopack, as you can see from these TST values, but there's a few that are slightly different. And then you can go ahead and actually make an IsoMap layer right from Zone Manager, like so, okay? In addition, if you want to use Zone Manager primarily to make your maps, you can calculate the vertical thickness of the zone, and you can simply map that vertical thickness. It's essentially the same thing as what we just did. Okay, just wanted to point that out. All right, now in many cases, and of course I go back to the days before computer software and we did all our contouring by hand, and there's still many users out there that believe that the best thing to do is to get the machine to give you the 80 or 90% solution and then go ahead and hand contour, hand tweak your contours, etc. To get your final version of your map. And in fact, there's still quite a few people out there, I reckon, that are starting from scratch, posting the data values and drawing their contours by hand. And GeoAtlas has quite a few tools that really facilitate this. Now, I'm going to go through a quick example of taking this map and show you how to go ahead and tweak it by hand. All right, I want to show you I'm going to give you a tip that can save you a lot of heartache, let's say. I've run into a few situations where people have worked for an hour or two on their map and then essentially destroyed their work by updating the layer unnecessarily. So I want to give you this tip. What I'm going to do is I'm going to copy the contours to a blank IsoMap layer and then underlay the data points with the values underneath the contours on that blank layer. By doing that, I remove the option you have to update your hand contoured layer, if you will, because there's no underlying data or grid, so you can't screw up. That's the bottom line. So let me show you that trick. So with my isochore being my active layer, I'm going to go to something up here called the entity filter, and I'm going to uncheck the other entities other than contour. This controls what I can select on this layer. I'll say OK, and now I'll draw a selection box around that bad boy, and I'll go ahead and edit copy all those contours. Okay, I've just got the contours now copied, and I'm going to go layers, create blank layer. It's going to be an IsoMap layer. All right, and I will call this layer with my initials hand edited Snyabar. Hand edited Snyabar contours. Okay. And that slaps that blank layer on top of the other layers in my map, so it's now the active layer. So now I can do an edit paste. Whoops, there we go, edit paste right there. So the contours on the clipboard I copied off of the machine generated map are now slapped onto that blank layer, and I can go to my Snyabar isocore layer and I can hide my contours with the eyeball right here in my layer selection dialog. So now I'm not seeing those double contours. And by the way, in case some of you aren't familiar with this layer selection dialog, which is a very handy little tool, you can get it to display by going to View, Toolbars, and then select Layer Selection. Okay. And it originally comes in kind of narrow and docked on the left like so, and you can release it from its prison by double clicking on it and move it around, make it, resize it, put it on your other monitor. If you accidentally dock it by hitting the top toolbar, you end up with a less than useful mapping interface. Double click on it and redock it, making sure you don't hit that lowermost toolbar, and you'll be fine. Okay. Now what I would now do is I would go into, I'll go into layer display attributes, and I'll go into my isocore layer, into my data points, and actually, there we go, turn quote unquote the elevation on, even though it's a thickness. The term elevation is always used, and then I can change the height of the elevation, etc. What I'm doing now is I'm posting the data in behind this guy. And now theoretically, let's see if I got it right here. Now theoretically I can come in here. Yeah, the elevations are still too small, but you can at least, or the thicknesses rather are still too small, but you can at least see them. And then if I wanted to go ahead and edit my contours, I could click on a contour and then hit the node editor right here, which allows me to drag nodes around. I can cut the contour line. I can chop out pieces and redraw it if I want. Let me click on this guy, and look at that. Click on the contour, click on the nodes. That's a lot of nodes. In fact, if I zoom out, you can see that to edit this contour, I don't necessarily want to drag individual nodes. I might have to use my eraser tool and erase nodes, but I do have another alternative. And by the way, we're actually working on an enhancement to where we can actually select a contour line and reduce the number of nodes on the contour line so that you can hand edit it more easily. Another option that you would have to reduce the number of nodes is to increase the smallest feature radius, i.e. drop the total number of grid nodes so you get far fewer contour nodes. It's a compromise in terms of the accuracy of the map in areas where you have a lot of tight data, but you can do that maybe iteratively and figure out the best setting, because again, the larger the smallest feature radius, i.e. the less detailed your grid, the fewer nodes you'll have on your contour line. So there's going to be some happy medium in there that'll allow you to effectively edit your contours without having to delete hundreds of nodes. Okay, but again, we're working on a solution for that. Now once you've edited your contours, it behooves you to go ahead and create a contour to grid layer. All right. In many cases, you might want to do, in some cases, you might want to do volumetrics, or you might want to use your layer, your hand edited layer that's essentially giving you the geologic interpretation you want, as a surface source in either our old cross-section tool. Let me go back out to full extents and zoom back in a little bit here. In our old cross-section tool or in our geomodeling tool, you can source excuse me, you can source your surfaces in our geomodeling tool, at least one or several, from grids. And so if you nail a particular surface or two by hand editing and then do a contour to grid, uh, it gives you a surface you can hang your hat on pretty nicely. And the way you do a contour to grid is in IsoMap contour to grid. And a couple of tips here real quickly before I move on to another project and show you one last example. You choose your source, in this case hand edited Snaibar contours. You have a new layer that you name, and you can just call it Snaibar CTG, contour to grid, whoops, whatever, you name it appropriately. And then I typically sample these contours very tightly. So essentially what's happening here is I'm sampling the contours every 250 feet. And then when I go through the layer create process, so it's sampling the contours. When I go through the layer create process, I go into build parameters, grid spacing, and again I want to reduce my smallest feature radius to something approaching my sampling. So again, I might use 500 feet. One comment, so in many cases people use contour to grid and they don't like the results. They say, hey, my contour to grid contours don't match my hand edited contours, and the reason is usually the sampling interval of the contours is not tight enough, or the smallest feature radius is too large, or both. If you're really careful about tight sampling and a smallest feature radius, you will generally get very, very good results. Okay, and then you get your contour grid layer. It's got a grid. The grid is essentially conforming to your hand edits. And again, you can then do volumetrics or do something like source that surface to source a geomodeling surface to that grid, and then use that surface maybe to constrain other surfaces. So maybe it's a target surface for your horizontal wells. Okay, and so you want to make sure that maybe the upper target surface is nailed by hand edits, and then you can constrain your lower target surface, so you're by that upper surface, and then your zone is really, really well defined based on your interpretation of the geology. Okay, now what I want to do, let me go ahead and close Zone Manager here. I want to do quickly is show you an example that I ran into. I actually got on my radar when a client said, hey, I'm not getting labels on my contours on IsoMap. What's going on? So let me quickly change to an AOI in another project. I know we're getting short on time here, so I'll try to make this example fairly quick. I'll change to this AOI and I'll open a map. So this is an actual example of a client's hand contoured map. There's a map here, trust me, it's there it is. I'm going to zoom in, and so the problem here, so you can see what the user's done, right? And obviously there's some faulting in here. The issue with regard to labeling these contours, and this is a completely hand-drawn map, so it was never machine generated, it's completely hand-drawn. The problem is that you've got contours. Here's a 2550, and then it's adjacent essentially to a 2050. So what you have is you have an irregular contour interval, and so IsoMap doesn't know what to do with that, and it's not going to be able to label the contours. We took a look at that. I said, okay, you've obviously got some faults in here. Do you have the faults anywhere? And so sure enough, there was a layer with fault traces with teeth showing the direction of throw. And I said, okay, what we need to probably do is create a contour to grid layer here using the faults. But the problem is that these faults, let's see, let me go to make sure that fault traces is the active layer. These are in fact fault traces. You see the active entity is fault trace. We have three types of faults. We have fault polygons, fault traces, and centerline faults. The only fault type that's not used in gridding and contouring by IsoMap is in fact fault traces. So what we did was we selected all the fault traces, and we can actually change the active entity to centerline fault here, and it will say, hey, you want to change the entity? And we said yes. So then we had centerline faults that would actually be used in the gridding and contouring operation. And the end result, let me minimize this map, the end result of that was a contour to grid layer incorporating those faults. Let me maximize that bit. There we go. And zoom in. And you got a pretty darn good result. There's a few places we need to clean up adjacent to the fault by maybe deleting some contours or hand editing them. But in general, this was a very high fidelity relative to the original hand contoured map. And notice, hey, it's labeling. The contours are labeling because by gridding, you let IsoMap take over. It fixes all the issues with irregular contour intervals, etc. And the same is also true if you want to do color fill contours on here. Color fill contours are particularly susceptible to broken contour lines, to irregular contour intervals, to contours that don't reach all the way to something like a fault or a boundary polygon. So by using the contour grid operation, you can really spare yourself a lot of heartburn and get your isomaps to look really good. Okay. Well, I know I've got a little bit over time here. I appreciate your attention. You can always contact our support group.